Okay, so welcome back to another video. So here's a definite integral from 0 to 1, and our integrand is consisting of a log-based function inside of a floor function. So we have that our integrand is 1 divided by the floor of 1 minus log base 2 of 1 minus x, and then followed by differential dx. So if we actually just use that definition of a floor function carefully and perform that substitution that we need to, eventually, as you see that this is actually going to convert this into a sum of integrals, eventually leading up to the fact that we're really just evaluating a sum. So we want to also be careful that because this is a log base 2, so we can't necessarily make sure not to get like the definition of both a natural log and a log based function confused in that situation. Interestingly, if you were to graph this integrand, of course, this is actually, for one, a floor function, so it's going to act like a piecewise function. But if you were to see that the bounds from 0 to 1, just like what we're integrating with, this is not only decreasing, but it's like when you're trying to calculate this area, and specifically treat this as an integral, it's like calculating the infinitely number of areas of rectangles as they get smaller and smaller and smaller in terms of the sub-interval length. That's actually a little bit difficult to work around with, but actually if we, in this standard way with substitutions, this is actually, a little bit more of a easier approach. So with that, let's actually just jump right in. So if we let u equals this inside of our floor function, so 1 minus log base 2 of 1 minus x, that if I were to differentiate both sides, so I have that du is equal to, the derivative of a log-based function, so log a of x, a for a base, for example, strictly greater than 0, that the derivative is supposed to be 1 divided by x times ln of a, that base. And so if we utilize that, so that means we would have this as 1 divided by ln of 2, and then multiplied by 1 minus x dx, but we can't do anything with this dx differential on its own because we have a du, so we want this by itself. So we would solve this out. We have ln of 2, then multiplied by 1 minus x. This is equal to du equals dx. And then we need to do something about this 1 minus x because everything's in terms of u. So if we were to solve this out from back here, then we would have, going from down here below, so I have 1 minus u, so what I do is just minus the 1 and then divide by the negative 1. And so we have log 2 of 1 minus x. But if we actually just treat this in definitions of how the logarithm base functions work, so this is 2 times 1 minus u equals 1 minus x. So therefore with this, 1 minus u equals 1 minus x, and I'll just substitute this back in for our new dx differential. So dx is equal to ln of 2, and then multiplied by 2 to the power 1 minus u, and then this is du. And so with that, now we can actually perform that little substitution that we need. And of course, we need to change our bounds of integration as well. So keep in mind not to forget that step. After performing all this, so here's what we're going to get. So our new bounds, we're going to start off. So the bottom is, if we plug in 0 back here, so that means this is 1 minus 0, that's 1. So log 2 base 1. All this is actually just going to become 1. And then from the top, we have 1 minus 1. So log 2 base is 0. That's going to actually have to approach negative infinity, but then that will approach to positive infinity instead. And plugging all this back in for the new differential, so we have ln of 2 multiplied by 2 to the power 1 minus u, all this being divided by the floor of u, and then put in du. And so from here, let's actually fix this up just a little bit, so in terms of simplification. For 1, so we have 2 to the power 1, so I'll factor that out. So it'd be 2 to the power 1 multiplied by 2 to the power negative u. So put this back here, so 2 times ln of 2, put that back as the exponent with natural log rule, so we have ln of 4, and so that's still constant, and so therefore I can move that outside of our integral. So ln of 4, our integral from 1 to infinity of 2 to the power negative u divided by the floor of u, and then du. Now with this, we actually want to do something about this floor function over here, dealing with the fact that this is actually, in terms of like a piecewise function, if we look at it in this sense. So by using by that definition, so I say that if for some natural number k, if we're looking at this from our interval, that means then that will have to mean that the floor of U is equal to K, such that, well, this is for K is in between K to K plus 1. So K is inclusive and then K plus 1 is non-inclusive. So with this, we can actually transform this integral above and write this again as a sum of integrals. So now what we have now is ln of 4, then we have the infinite sum. So this is infinity. We can start with our index at k is equal to 1. And so we would have that for each step, this is going to go from k and then all the way up to k plus 1 of 2 to the power negative u, and then divided by k, multiplied by the differential du. And so with this, now we can easily take the integral of this integrand over here. So some constant to a power exponent. So this is basically just, we use the rules. We have, let's see, ln of 4, and put this back as infinite sum, then k is equal to 1. Then back here we would have that antiderivative if you actually follow with the u substitution as well, and then use the antiderivative of the a to the power u, a for a constant. So we have negative 2 to the power negative u, and then divided by k. K is still constant, keep that in mind, and then multiply by ln of 2. Evaluate this from our bounds from k plus 1, or k to k plus 1. And then this is actually an easy calculation to do. For one, before we get to that, we can actually do something with the ln of 2. So let's move that outside of our, our summation as well. That's also constant. Further implying that we can actually simplify the ln of 4 divided by ln of 2. Ln of 4, remember back then we wrote that that's the same thing as 2 times ln of 2. So undoing that, and so that'd be 2 times ln of 2 divided by the ln of 2, and so that would have to mean that that would be just positive 2. But also can also factor out that negative from over here, so it'll become negative 2, and then we have our infinite sum over here, and then all we have left now, it's actually just positive 2 to the negative u, and then divided by k. Evaluate from k to k plus 1, which is pretty standard to see that it's just plugging in and then subtraction. And also adding to another rule that we're actually jumping one more step, that I can actually evolve this into a linearity of 2 sums. And then if distributing a negative 2 carefully and correctly, so we have a minus 2 to the power, or negative 2 multiplied by this infinite sum of 2 to the negative k subtract 1 divided by k, and then minus again from that negative 2. So that's a positive 2, and then instead of k plus 1 for substituting, this is going to be k. So this is 2 to the power negative k, and then divided by k. And so now what I can do here is do a little bit more simplifying, specifically for this sum over here with the k minus 1, because what I can do is this is treated as 2 to the negative k times 2 to the negative 1. Move that outside, move the 2 to the negative 1 outside, that's still constant, so that's basically just 1/2. And so negative 2 divided by 2, that's just negative 1, so that makes simplifying things a little bit easier. So this is negative, and then k is equal to 1, then 2 to the power negative k divided by k. Add this back with the unchanged infinite sum over there. And this actually comes out nicely because it's under the same series, and then this is just constant, so I can actually perform some, addition to it. So that means we're actually back to just a singular of that infinite sum. So just 1 times the infinite sum of 2 to the power negative k divided by k. And so the last thing here now is how do we actually approach this? Well, what we can do here from as the final step, rather the final formula we can use here is we can actually use the Maclaurin series of the following function. So this one we will be using ln of 1 minus x, which says that ln of 1 minus x is going to equal this infinite sum. And this is the negative, so let me actually fix that and write the negative. So negative the infinite sum of, so k is equal to 1, of x to the power k divided by k, and it's such that x is in this interval, inclusive for negative 1 and then non-inclusive for positive 1. And this is nice because if you take a look at this is actually at the exact same form, and if we look at this input, this is the same thing as 2 to the negative 1, which is 1/2. So it actually indeed satisfies this condition that we can use this formula. Awesome. So that actually finishes up everything that we need to do. So if I go back and you apply this formula, so that would have to mean this infinite sum of k is equal 1 of 2 to the negative k divided by k, which is equal to just negative ln of 1. So it's basically because that's negative, just divide negative, and then we get that same equality from here. Then subtract with our x input, in this case 2 to the negative 1, or 1/2. Then in other words, this is just 1 minus 1/2, which is negative ln of 1/2. Then in other words, you can write this in terms of the natural log properties as with division. So this is subtraction negative of natural log. So ln of 1 minus, and then minus, so that'll be a plus ln of 2. And so therefore, ln of 1 is just 0. And so our final answer of this integral over here is going to equal just the natural log of 2. And just like that, we are done. As simple as it is, well, in this sort of a situation, if you're going to go for that method as mentioned, that if you graph then you take the infinitely amount of rectangles underneath that graph, you'll be stuck there for a while. So here we have it. So yeah, that's pretty cool if you ask me.